All right, let's dive right into this explainer. Today, we're unpacking something literally mind-bending. We're looking at how a microscopic, physical hardware gate inside a computer chip is being used to solve a massive, civilization-scale problem in artificial intelligence. Because you see, this isn't about some flashy new software app. It's about fundamentally rewiring how machines trust each other, right down at the speed of light.
So what happens when AI agents just can't be trusted? This right here is the absolute most crucial question facing the tech industry today. We're hitting what analysts are calling the AI Capex Wall. We're building these massive fleets of autonomous agents to do our heavy lifting. But what happens when you actually let them loose? How do you know for sure they're doing exactly what they're supposed to do and literally nothing else? Bottom line, if you can't trust them, you simply can't deploy them. And that brings us to a huge disconnect in the market. We are throwing tens of billions of dollars into a massive CapEx bubble to build faster, smarter infrastructure. But the missing link? We are completely ignoring the transaction cost of auditing these agents. We're basically building fleets of Formula One cars, but we completely forgot to build the paved roads and the traffic lights to keep them from crashing.
Section 1. The AI Capex Wall and the Latency of Trust. Let's break down exactly why this is happening and why this bubble has to correct. Look, trust requires latency. That's just a fundamental reality. Right now, autonomous agents are essentially trust-stateless. That means enterprises have to constantly route traffic all the way back to the cloud just to check if an agent is still playing by the rules. It's kind of like doing a full manual background check every single time an employee tries to send an email. It's incredibly slow, and honestly, it completely destroys the ROI of using agents in a high-speed machine-to-machine market.
Section 2. Zooming in on the Ballistic gate. Let's strip away the cloud layer and zoom all the way down to the raw silicon to look at the physical solution to this software problem. Enter the Ballistic gate. This is the hardware primitive we're focusing on today. It's brilliantly simple. Two 64-bit signatures go in, and one Hamming distance, which is just a precise measure of the difference between them, comes out. And I really want to emphasize this. This isn't some theoretical concept from a white paper. This is a deterministic receipt read straight off a standard ARM64 computer chip using native hardware logic. It is proven purely on the metal.
And you've got to look at this number, 0.5367 nanoseconds per driven comparison. That speed is almost incomprehensible. And the kicker? This latency is captured unprivileged. That means it requires absolutely zero root access to the machine, so you can securely deploy it right into any standard enterprise sandbox.
What I love about this source material here is the radical honesty. By pulling the data directly from raw counters and binary disassembly, they prove this gate is operating near the absolute physical floor of commodity silicon. They aren't relying on some magic single instruction. The scalar's 64-bit pop count actually lowers to fundamental hardware instructions like EOR and Neon, and the scaling is beautiful. If you wanted to go faster, you don't build more complex logic, you literally just print more parallel lanes on the silicon.
Section 3. Hardware as the unforgeable witness. Okay. So how do we actually harness that nanosecond speed to build something unhackable?
To figure that out, we map the latency hierarchy of the chip's cache. They do this using an unpredictable pointer chase. Basically, it forces the hardware to stall and reveal its true physical transit times because spatial prefetchers simply cannot guess what's coming next. Notice that massive jump from just 1.8 nanoseconds in the L1 cache all the way up to over 151 nanoseconds in the DRAM.
The data here spells out the stakes perfectly. If your agent stays in its assigned L1 cache, it takes 1.8 nanoseconds. But if it steps out of bounds and has to fetch from DRAM, bam, a massive 83.9 times physical penalty. That right there is what creates a real, localized fingerprint of the hardware. Software can be tricked, but physics doesn't lie.
So to capitalize on this, the developers made an absolutely fascinating architectural choice. Normally, graph exploration software keeps a giant visited set in memory, which ends up dragging everything down into that slow DRAM. This system, it drops the global visited set entirely. The working set is kept incredibly tiny, fitting perfectly into an 1152-byte L1 buffer. By dodging that memory tax completely, the hot loop literally never leaves the fastest part of the chip, sustaining an unbelievable 7.59 million walks per second across 10 cores.
Section 4. Ensuring role continuity. All right, we've got this nanosecond physics playground mapped out. How does this translate into an agent's actual identity? It gives us something called role continuity. This is the bridge from raw hardware to real-world utility. Role continuity means an agent's identity, its competence, and its intent are mathematically guaranteed over time without ever needing a slow, clunky software audit. We are taking trust from being this fuzzy, abstract software concept and turning it into a hard, physical boundary on the silicon itself.
The big takeaway here is that the semantic identity of the AI agent is physically mapped right to the geometry of the cache line. The agent doesn't just promise to behave, it is literally bound to its lane. Any out-of-lane drift instantly causes a cache miss, which is caught on the metal by our half a nanosecond gate.
Section 5. The economics of trust. Let's zoom back out to the macro level. How does a physical hardware witness actually save companies millions of dollars? Well, take a look at the efficiency of a standard enterprise data pipeline today. Because we're constantly stopping to audit these agents, a staggering 76% of an agent's signal just degrades into unpriced noise. You're only keeping about 24% of the actual signal. That 76% is pure friction, and it's exactly what this hardware needs to measure and price.
And that is where the math hits the balance sheet. For a large enterprise, that unpriced noise represents a massive vulnerability. The safe floor, meaning what you can manually defend line by line, is only about $760,000 per contract. But when you aggregate that, you're looking at a target of around $152 million in annual trust debt exposure. That is unverified agentic Capex just sitting there. But by using the Ballistic gate, you can actually convert that dangerous drift into a mathematically priceable boundary.
Section 6, the zero latency economy. Which brings us to our final macro thesis, a total paradigm shift in how digital markets will operate. Follow this logic chain with me. It's pretty wild. Step 1, we start with a physical hardware anchor. Step 2, that anchor mathematically guarantees role continuity. Step 3, because we have role continuity, we get instant intent verification, totally bypassing software audits. And step 4, when the cost of verifying intent drops to absolute zero, you unlock the zero latency machine economy. Compute and labor can infinitely specialize and trade with each other at the literal speed of light.
Think about what happens when the current AI hype bubble finally pops. All those vibe-coded software wrappers, they're gonna get wiped out. Regulators simply cannot govern hallucinating black boxes, but they absolutely can govern physical boundaries. They're going to demand deterministic hardware receipts. And insurance underwriters, they don't price vibes, they price bounded risk. The only agents left standing will be the ones grounded in verifiable silicon. I absolutely love this quote from the source material because it really just hits the nail on the head. This is not another AI tool. It is the fundamental hardware infrastructure for a zero-latency economy. They aren't trying to build another SaaS product. They're establishing the literal physical bedrock required for autonomous agents to exist safely in the wild.
So I'm going to leave you with this final provocative thought to chew on. As you watch billions of dollars pour into AI infrastructure, ask yourself, when the regulatory hammer inevitably drops, are your autonomous agents running on verifiable, insurable silicon? Or are they just out there generating millions of dollars of unpriced noise? It's a question we're all going to have to answer, and very soon. Thanks for joining me on this explainer. I'll see you next time.